All right, if we're going to talk about discrete random variables, we can, up till now, we might have tossed a coin 3 times and we've just listed the outcomes, haven't we? We've sort of drawn our tree diagram. And then we've just listed all the outcomes, sort of, let's get rid of that. Sort of a head, tail, assuming, we've got our head, tail scenario. And we could go head, tail, tail, etc. All right. So that's actually a probability distribution. Whereas what if instead of recording the actual results in that manner, we instead decide, okay, I either get 0, 1, 2, or 3. Since we're counting heads there, we'll do heads. Because then a head is just the same as 3, and the probability of that is 1/8. The probability of getting 0 heads is a tail, tail, tail. The probability of that is 1/8. And we could work out these two here, and they would both be 3/8. So x is equal to the number of heads. All right, so that's my distribution, and my distribution has certain kind of features. The probabilities have to add to 1. Okay, sum of the probabilities is 1. And the other big one is all the probabilities are greater than 0. Because 0 means it can't happen, 1 means it must happen. So you're somewhere in between. All right. So that's what my probability distribution has to look like. So we can represent our distribution in a couple of ways. We could have a graph, okay, which I haven't got an example on. We could have a rule, like this one here, okay, or we could just have a table. All right, and invariably it's a table that we tend to come up with. So if we have a look at the rule first, though, we're saying the rule for the probability of x is given by 16 over 15x, and we're saying that x can be 2, 4, 8, or 16. Okay, so if x happens to be 2, if I put 2 into the rule, I get 16 on 30. So if I just get a common denominator for all of them, 2 on 30 is the same as multiply both by 8, 128 on 64. If I put x equal to 4, 4 15s are 60, I get 16 on 60. Multiply by 4, I get 64 on 240. If I put x equal to 8, 8 15s are 120, and that's the same as 32. Oops. 32 on 240. Then finally, if I put x equal to 16, 15 16s are 240, I just get 16 on 240. So if that's right, if I add up all them, 128 plus 64 is 192, plus 32 is 124, plus 16 is 240. They all add up to 1. They all add up to 1. They're all greater than 0, so that's a probability distribution. And it's a rule for a probability distribution. So if we look at these examples here, which of these are probability distributions? Well, let's have a look. 0.2, 0.3, 0.4, 0.1 adds up to 10, so that's equal to 1, and they're all positive, so no problems there. 1/3, 1/3, 1/3, they're all greater than 1. They're all positive. They add up to 1, no problems there. Negative 0.2, 0.4, and 0.8 adds up to 1, but you can't have a negative probability, so no good there. All right. So this is just my table of probabilities. It's sort of, if in some ways, it means we don't have to try and calculate them all. So what's this next example we've got? We've got a spinner numbered from 1 to 8, and each outcome is equally likely. So the chances of getting a 1 is the same as getting an 8, I have 8 possibilities. Each number's on the wheel only one, so each probability is 1/8. So 1/8, 1/8. So each probability is 1/8. So that's my probability distribution. Okay. And then we can use my distribution table to try and answer some probabilities. What's the probability that x is equal to 5? Well, there's 5 there, 1/8. What's the probability that x is greater than or equal to 4? Greater than or equal to 4 are those 5 numbers there, and each of them are 1/8. So that's 5/8. Probability that x is strictly less than 4 are those 3 numbers, probability of a 1, a 2, or a 3. That's equal to 3/8. What's the probability of a number strictly greater than 3 and less than or equal to 7? So greater than 3, which is there, but less than or equal to 7 is that one there as well. So there's 4 numbers there, isn't it? 4, 5, 6, and 7. So we'll call that 4/8, which we probably should simplify to 1/8, 1/2. The final one there is x is equal to 5 given x is greater than or equal to 4. So that's my conditional probability. So remember, the probability of A given B is equal to the probability of A intersection B over the probability of B. So with that in mind, what is A intersection B? That means it's got to be the probability of x equaling 5 and x greater than or equal to 4 over probability of x greater than or equal to 4. Now, what numbers satisfy the top line? What numbers are equal to 5 and greater than or equal to 4? Well, it's really just one. That one there. So it's a probability that x is equal to 5, and the probability that x is equal to 5 is 1/8. And what's the probability that x is greater than or equal to 4? Well, that's the answer to the second question. That's 5/8. So the final answer is 1/8 over 5/8, which is times, flip it upside down and multiply, 1/5. Okay. Yeah. What about a bias coin such that the probability of head is equal to 0.7? Find the probability distribution of x, the number of tails where the coin is tossed twice. So my probability distribution looks like that. I get 0, 1, or 2 heads. That's x. That's the probability that x is equal to x. All right, so what's the probability of 2 heads? It's just a head-head, 0.7 by 0.7. So probability of head is equal to 0.7 by 0.7, which is 0.49. Probability of tail is going to be 0.3 by 0.3, because if the probability of getting a head is 0.7, well, the probability of getting a tail is 1 minus that. 0.3 by 0.3 is 0.09. And we only have one probability left, so that 0.09 plus 0.49 is 0.58. So the answer should be there, 0.42. Let's check. That answer should be the probability of a head then a tail, or the probability of a tail then a head. And that's 0.7 by 0.3 plus 0.3 by 0.7, 0.21 plus 2, or 0.21 times 2 gives us a 0.42. Okay, so that's my probability distribution table there. What about a spinner that's labelled 1 to 4? it's spun twice. So what does that mean? This is the sample space. That means I get a 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1. It's a bit time consuming, but just list them out when we're asked to. 4, 1, 4, 2, 4, 3, 4, 4. Right. Now, find the probability distribution of x, the sum of the two numbers. So what we want to actually record here is what the two numbers add up to. So what are the possible answers here? Well, the lowest answer is a 1 and a 1, so it'll add up to 2. And the highest answer is a 4 and a 4, which adds up to 8. So probability that x is equal to, big X is equal to little x. So how many ways can I get a total of 2? There's only one, and that's 1, 1. So that's 1 out of 16 different outcomes. How can I get a 3? 2, 1, and a 1, 2. 2 out of 16. How many ways can I get 4? 3, 1, 2, 2, 1, 3. So by having them all listed, 5, it's very easy to count up 6 back to 3. It's very easy to count up the different number of possibilities. If I've done it right, 1 plus 2 plus 3 plus 4 is 10, plus 3, 2, 1 is 16. They all add up to 1, so I'm pretty confident I'm on the right track. And then we can use that table to answer any questions we want. What's the probability of a number greater than 4? What's the probability of a number between 2 and 6? Or in this case, the probability of x is greater than 4 given x is less than or equal to 6 is my conditional rule. X is greater than or equal to 4 given x is less than or equal to 6 is equal to the intersection over probability that x is less than or equal to 6. So what numbers are greater than or equal to 4 and less than or equal to 6? Well, that's the same as saying less than or equal to 4. Whoops. X is between 4 and 6 over the probability that x is less than or equal to 6. So what's the probability of a number between 4 and 6? Where's that? 4, 5, and 6, which is 3 and 4 and 3. That's equal to 10 over 16, all over a number less than 6. A number less than 6 is those 5, which is 3, 6, 10, 13. Flip upside down and multiply. So the probability of that happening is 10 on 13.